Okay, so good evening, everyone, and welcome to today's Asset Colloquium. And as you would have already noticed, so today's colloquium is going to be a bit in the hybrid mode, namely to say that we have the actual speaker speaking from AG66, our usual venue. But of course, the online platform continues for some more time. And another speciality of today's colloquium is also is our speaker, Mr. Simon Pereira, also going to show you some of these beautiful devices that they have built in Gauribidanur as part of the torsion balance experiment. And so, of course, the title of the talk is Instrumentation for Torsion Balance Experiment. So without taking more of his time, I invite Professor Unnikrishnan to formally introduce today's speaker, Unni.
Yeah, so I have the very pleasant job of introducing my friend and colleague, Simon Pereira. Of course, for somebody who has been in the institute for more than 30 years, may not make much sense to introduce. However, I have been in this institute for slightly longer time. In fact, fit to be what I would call the dean introductions. So I will try to introduce Simon for the purpose of this talk. Simon joined the gravitation experiments group early in the work of that group, which was a small group, including me. And we all grew up together building instruments for gravitation experiments in a field station environment. So we are like family members working together for a physics experiment. And Simon's involvement has been very, very important as a practical problem solver and an instrument maker. He has been very successful in making reliable measuring instruments, electronic instruments for this experiment. In fact, some of those instruments have been working for 30 years. So Simon's expertise is in electronics, analog electronics wiring and electronics design. But he has also taken some lead in understanding the principles of experiments with relevance to gravitation and try to make his own contributions and innovations in handling this precision instruments, which he will talk about today. What is so impressive for me in Simon's activities is involvement with passion, trying to innovate an idea further with his own ideas, and the discussions he brings up in that context have helped us also to be more clear in some of the concepts in dealing with such experiments. So with this introduction, I invite Simon to talk about gravitation experiments and precision measurements.
Thank you, Professor Unnikrishnan, for this nice introduction. And good evening to all those who are in presence in lecture theatre and those who are watching on Zoom or YouTube. It's a great pleasure to give a talk in AG66 always, though we have been hampered by the pandemic. This is the first step in the opening up. Today, I'm going to talk about the instrumentation for torsion balance experiment. There are various aspects of the torsion balance instrumentation which needs control systems. In the year 2012, I talked about in this very asset forum about the thermal control system for the torsion balance. Today's talk is mainly related to the automation of the various processes in the experiment. In fact, the automation is been forced, but the need for the automation was strongly felt because of the successful commissioning of the thermal control system at the Gauribidanur field station. So I'll be taking you to the journey of this automation process. Here is the outline of my talk. I'll give introduction about the experiment with torsion balance. Then I will talk about the control instrumentation developed for the torsion balance. I'll show a few measurements from the prototype setup at Mumbai lab. These measurements are carried out for testing purpose, for the control of the system and the data exchange system. And I will sum up with the summary of the work done. So let's begin with the introduction. The first question comes to mind, what is a torsion balance? A torsion balance is a scientific apparatus used for measuring weak forces. A torsion balance has a beam or a disc which is suspended from the middle by a thin fiber, and the fiber acts like a big torsion spring. And the sensitivity of the instrument comes from the big torsional constant of the spring. So for a small force, there will be large rotation of the beam. So torsion balance, the history of torsion balance goes back to almost 2 centuries. The invention of torsion balance is attributed to Coulomb. He invented somewhere in 1777, but also by John Michell independently somewhere around 1783. Coulomb used this torsion balance to measure the charge between two charges, and which led to Coulomb's law of electrostatic, which is given by here. While Cavendish used the torsion balance for measuring the force between two masses somewhere in 1798, which led to the value of G. Eventually, he found out the value of big G. So torsion balance has been there around for past 200 years, and they have been used for doing very minuscule forces, small forces, especially of gravitational nature. The measurement of such forces aim at testing some of the fundamental theoretical assumptions, like proving the weak equivalent principle or the inverse square law of gravitation, or for the precision of the big G value. Gravitation group of TIFR at TIFR has been involved for past 40 years in study of gravity as a fundamental interaction. The recent activity of the group was centered around the test of equivalence principle. So what is the equivalence principle? Equivalence principle in sense goes back to Galileo and Newton, who asserted that in a gravitational field, all bodies fall with the same acceleration, regardless of their mass, composition, or size. In a simplistic way, it can be stated as the inertial mass and the gravitational mass are the same. This equivalence of the gravitational mass and inertial mass is assumed to be the one of the most fundamental principle of nature. And hence there is a strong motivation to test this principle with highest possible precision. We conduct our experiment at a dedicated site in the state of Karnataka, a place called Gauribidanur, where a specialized laboratory is built underground. Here is a wellhead building of the lab. Superimposed is the underground laboratory, which is 80 feet deep. Our instrument lies at the bottom of the well, which is enclosed in a thermal enclosure, and the last part of the well is covered by a dome for thermal isolation. And as you go up, we keep on isolating this instrument from ground noise as well as thermal noise. As demanded by the equivalence principle, we built and successfully completed the thermal control system with the aim of stabilizing the ambient temperature to 1 millidegree centigrade in a volume of 30 meter cube area. The control has to be operated for several days. So here is a photograph of the full system, which is 8 meter in height and 1 meter is panel, which is covering the entire apparatus at the bottom of the underground laboratory. What you see here is a third level, which we seal with a flange and a dome, so the entire thing is covered and hermetically sealed. Our thermal controls has been very successful, and it has delivered the performance much beyond our goal, which was 1 millidegree, but we went to something like 0.6 millidegree. And is operated for several days. To our knowledge, this is a unique system which at sheer volume and the level of control we have achieved. But at the same time, the thermal enclosure, which encloses the apparatus at underground, that is a UHP system, and the associated instrumentation there, has restricted our access, especially in the initial integration of the experiment, alignment of optics, and control of motion of torsion balance. So what is the motion of torsion balance? Just to give an idea for the audience who may not be familiar with this. The torsion balance oscillatory motion is caused by restoring torque, which is proportional to the angular displacement theta. So it's a simple harmonic motion governed by this second order differential equation, and the incident angle theta is given by this equation. And the angular frequency omega depends upon the torsional constant K of the fiber and the inversely proportional to the inertia of the pendulum. The signal we seek for the test of equivalence principle is the modulation of the simple harmonic motion by a 24-hour period, and the amplitude of modulation will be of the order of 10 to the minus 10 radian. Since the torsion balance is very delicate device, some non-contact method should be used for the measurement of this angle. We monitor the balance motion by optical lever. The principle of the optical lever is like this. Light is incident on a mirror and reflected back on a suitable detector. As the mirror rotates, the light spot translates. And one can measure with this silicon detectors, the smallest displacement of linear is about 0.1 nanometer. So at a distance of 2 meter incident, one can reach or attain the resolution of 10 minus 10. In our experiment, we have a torsion balance in horizontal dipole configuration assembled in an ultra heavy vacuum chamber. suspended by a fiber, which is cross section is 25 by 15 micron, and the length is 3.5 meter. Our torsion balance has a 2 half semicircle of 2 different materials. This is lead and copper, balancing Earth's gravitational force and falling into Sun's gravitational force. So the Sun is the source of attraction force. If the ratio of gravitational mass to the inertial mass of these 2 test bodies are different, then there will be a twist into the motion of torsion balance. That is, the mean position will be shifted, and that is the 24-hour signal what we were looking. For monitoring the motion, we have a mirror here, which is a 4-sided mirror. One side we use for the actual measurement of the angle, while the other side we use for the control application. And I will talk about that. So I will be mostly concentrating on the control part of the torsion balance motion. Of course, there will be measurements associated with that. We use optical lever for providing high resolution of angle measurement. There are 2 of them. Our primary optical lever has a resolution of 3 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ half 5 microradian, while the secondary optical lever has a resolution of 5 microradian and the operating range of 6 milliradian. I hope I have given you enough introduction about the experiment and the measurements we want to do. So we have got an idea that what kind of resolution of the optical lever we have to reach. Now where the motion control comes in picture. So that's where we have to develop an instrumentation for controlling the motion. So what is the need of instrumentation for controlling the motion? The initial amplitude of torsion oscillation is often quite large. It will be tens of degrees to several full rotations. That is, you can have 2 pi, 4 pi, depends upon the twist in the fiber. And the fact that the natural damping for a good torsion pendulum system is often very low. So this is one. The another thing is the angular orientation of the axis of the optical lever, which is facing to the mirror, may be offset from the direction of the normal to the mirror. So one has to accomplish two jobs. The first one is to observe the complete motion of torsion pendulum. The amplitude of oscillation has to be less than 5 microradian, and the orientation of the mirror has to be adjusted according to the configuration of the optical lever. So to do these two tasks and subsequently the calibration, we have developed the instrumentation, and moreover we have automated this whole process because we cannot go underground inside near to our instrument and do any measurements. So I will show you what is the instrumentation we have developed. For this presentation, I have divided this instrumentation in 4 parts. The first one is image alignment. The second is amplitude damping. The third is auto-calibration. And fourth is drift correction. And they all are interlinked in some ways, but they will be sharing some hardware piece common in various ways. Let us focus on the very first thing, which is image alignment. So this will be done by using two components of the system, top feed through and the beam steering mirror. The total height of this apparatus is about 6 meters, because the fiber itself is 3.5 meters, and then you have the pendulum, the upper header part, and below table. So at Gauribidanur, we have an experimental apparatus. This is a UHE chamber, is almost 1 meter diameter. This is half the portion of this. Since I cannot picture it in one photograph, I've been showing in a 2 photograph. And this is the top. And this total height from here to the bottom here, the table is not shown, which is at the underground level, is around 6 meters. On the top of the UHV header pipe, we have vacuum compatible fit through assembly, which allows us to initial operation with the balance. So these are direct in contact with the balance, and these are used for the coarse adjustment. And these adjustments are adjusting the vertical position of the mirror assembled fiber and damping of very large amplitudes of torsion balance oscillation. Right now, we'll concentrate on adjusting the vertical position of the mirror. So the vertical position of the mirror has to be adjusted in the field of view of optical window of the UHV system. As I said, this is a 3.5 meter fiber, and there are various parts into it on top side. So you are not sure the whatever best you calculate, there will be weight of the torsion pendulum, which is around 1.5 kilogram, will be stretched in the fiber. So we make sure that visibly that mirror remains in the top half of the window, so that even if it gets stretched, it will be somewhere in the middle. This is achieved by using the linear transfer mechanism of the top header assembly. So you see a stepper motor here, and there is a gear down box, and the other side of that there is a bellow which opens up or contracts. It has a certain limited range, and we use stepper motor controller, which is home built, and a software which is developed for our application to accomplish this job. So here we can select which motor you want to use, what speed you want to add, which direction, which mode, everything, which is software programmable, and one can make use of this thing visibly by seeing at the mirror. The exact position of the image is accomplished through a 45-degree beam steering mirror. So you have a detector here. This is our secondary optical lever, which is used for the control application. So we use a 45-degree beam steering mirror driven by motor micrometers to translate the beam to get in close onto the detector. So how we do that? You are not sure where your image is. You have done the manual adjustment on the field of view of a mirror and left it. Now it is accomplished by driving this motor mic in a certain fashion, like you use up-down motion to translate the image up and down, and use another one to translate the image in horizontal direction. So in first case, you just go in a step. You can decide what step you want, displacement like 1 millimeter or 2 millimeter. You decide what the displacement you want, vertical, and you decide whether up or down. These are the choice given to you. So you keep on moving it in one direction and look for the transition of the image. The moment it hits onto one of these detectors. So you see there are 2 extra detectors here, which are integrated to this focal plane. If it hits this detector from down, we know that the image has to move up. And if it happens to be hit on this detector, we know that it has to come down. And we know precisely how much now we have to move. So that you can program it so that it ends up into the center of this. It hits both the detectors that ensure that it enters at the center of this detector, horizontal detector. So what you see is a signal like this. Now you may be wondering, this is the motion of a torsion balance. Yes, it is. And this will be the case when you release the torsion balance from its cradle into the ultra high vacuum chamber. And this is a high Q system. So it takes a long time, very, very long time for the self damping. So these are the transition of the image onto the detector. The red and blue are from the vertical detectors, and the green is from horizontal detectors. Now you say multiple transition because we have the 4-phase mirror. So from each phase there will be a transition. So you will be getting. So this is a total period of roughly 900 seconds. This particular pendulum, which is in operation at Mumbai, has a period of 860 seconds. The one in at Gauribidanur has something like 33 minutes. So for one transition, you have to wait for that much time. Imagine if you are at the underground laboratory doing these measurements. So once you make sure that your image is transition onto the detector, the next thing comes up with the damping of this motion. So I'll move on to the second part of this. Amplitude damping using again the top feed through, which is used for the large amplitude damping. Here, the oscillation of very large amplitude are damped down by mechanical techniques. That is called a sudden shifting of potential wave. Now here I would like to do some small demonstration. What is this potential wave and how we shift them? Can anybody respond that I'm visible?
Yes.
Yes, you are visible.
Okay. Can you see there is some simple pendulum?
Yes. Can you lift up a little bit?
I have to use background of my trouser, otherwise you will not see that ball.
Ah, got it. Okay.
So it's at the center now. If I pull it there, I have stored some energy into it, which is the potential energy, right? And I release it, and it keeps on oscillating, and it will keep on doing till it naturally damps. What I do in the sudden shifting of potential wave. So again, I will demonstrate it. So I take it here and release from here, and it goes doing. If I shift this here and shift it here, it will stop. Let me again do it. So that's it. So you shift it twice. You have to take to the left, again bring to right, at the right time and right amount. Okay, that is called sudden shifting of potential wave. In case of torsional pendulum, what we use to do this is the top rotary feed through. Here is the component of that assembly, which is the top. What we do, a set of precise time rotary motions, as you see in case of a simple pendulum, you can rapidly damp down the amplitude. But the crucial thing is the drive parameters for stepper motor. That is the angle, how much to move, direction, whether clockwise and anti-clockwise, and start time of the motor. If you do at wrong time in wrong direction, the amplitude will grow. Now, how to know what is the angle and which direction it is coming and what time to start? These are the crucial parameters one has to find out. So here is the principle of measurement. I think I will not go into too details of this mathematical. Rather, I will prefer to do one more small demonstration. I don't know whether this will explain the well, but for all of us, we know one angle for sure is a full rotation of a circle. So suppose you have a circle here, there's a pointer here, and if I move it here, you know it has completed one circle and some angle. All of us say that it has gone to 360 degrees or 2 pi radian. Or other side it has gone, again, one full circle and slightly more. So if you know the time instant of this one full circle 2 pi on either side, that information one can use to determine what is the amplitude, that is the peak-to-peak amplitude. And that's what is done here. So look at it. This is the mirror over here. So here is a 4-phase mirror. The phase 2 was supposed to be aligned with the optic axis of the optical lever, but it is offset. So if it is moving from here, what it's going to do, it is going to hit the detector first and then go all the way one round complete like this. That is 2 pi. So you get an angle which is 2 pi plus theta 0, which is the offset. You start from here, you go all the way here and you go beyond. Okay. And this is the theta 1 at this position. Similarly, if you reverse, you go back, again hit. So you're coming back from here. Now you're coming to this optical before it's hitting to the 2 pi. So it is 2 pi minus theta 0. So you got theta1, you got theta2. What you do is you do theta1 minus theta2. So do theta1 minus theta2, what you get is a 4 pi. And you do theta1 plus theta2, you get 2 theta0, which is the offset. So all you have to do is this substitute values for theta1 and theta2. But how to know what is theta1 and theta2? That is found out from the t, that is the period, and t1, which is delta t1 by 2, that is the instant of time here or here, and t2, which is time here or here. If you know this t1, delta t1 and delta t2 and the t by 2, you will know all the parameters to put into the equation, and which will give you the amplitude of this thing. So all you have to need to know is this t1, t2, t3, t4, and that's what been implemented in our measurement scheme. So as I said, this is an optical lever which is secondary used for the control application. There's a lens over here, there's a focal plane, and on focal plane we have these horizontal detectors and these two vertical detectors. See, we use this vertical detector initially for alignment of image. Now the same vertical detectors we are going to use for the amplitude damping. You might have noticed that they are displaced vertically and horizontally. So there's a purpose behind this. As I explained, in case of vertically, you will know which direction the image is coming. In case of horizontal, they give us the direction information first of all. That if it's coming, this detector will hit first. If it is coming from this side, this detector will hit first. So you know whether it is clockwise or counterclockwise. That is one thing you get here. Also, you will find out the turnaround time. If it hits on this detector, goes back and comes back again, then you know the instant of time hitting twice here, which will give the turn time. And most importantly, that if you find out the offset with respect to the mean position of the torsion medium, offset for this and offset for this, then you get the angle between these two detectors, which is our calibrated angle. See, by knowing the 2 pi angle, we can find the amplitudes about 2 pi and above. What about the angles less than 2 pi? For that, we have to have some calibrated angle, which can give us a hand or a tool to know all the angles, all the way from 10 radians to 0.1 radians or below. So, as I shown you earlier, now this is the signal only for the one mirror transition. Again, you see that is the 900 seconds is the period of this thing. And if you blow up and see, this is what it looks. This is on detector 1. This one first, the detector 2, red one, and the green is the horizontal detector. Time being, you just forget about this. This is the behavior of the amplifier and the integrator and things like that. We cannot make use of this for the direction as well as for the amplitude. But we can use of this to transition time to get the information. So this information of time has been captured in a program, and here is the output of all those things. So like here we get the transition of detector 1 or transition of detector 2 here. So you find out the turn time by D1, turn time by D2. The turn time should be the same, and they're more or less, they're within 4 millisecond accuracy. They're both are saying that it has done the same time. It's the good news. The period what they show also within 1 millisecond, 859.426, 859.425. That is also good news. The amplitude also they are doing the same, 6.658, 6.658, very accurate. But the offset they are reporting are different, and that's what we want, because they are offsetted at different position from this mean. So the angle between them, if you subtract this offset, you get the angle between them, which is 12.4 milliradian. And if you measure the distance between these two detectors, it is close to 12.5 millimeter. So this gives a calibrated angle, this gives the turn time, this gives the all the parameters required. So this information is used first to get a calibrated angle by driving the torsion pendulum beyond 2 pi radian. Now, whenever there is any amplitude, we can use this calibrated angle to find out the amplitude. And here is what it is done here. Now you don't have to worry about that full oscillation cycle. All you have to know is the transition time at D1 and transition time at D2. And that gives the amplitude, that gives the offset, that gives the turn time, and that gives the next turn time. And all this information is passed to a stepper motor controller within the program. This is automated everything. It knows what direction to drive, like counterclockwise first, at what time, at 16:08. The next turn will be at 16:15 and direction clockwise. So here, the first instance where you do the measurement, the second instance where you apply the control. Now we see here that on the horizontal detector, which was earlier like this, has become this way. So it is more or less on the detector, but going out of the detector. And this because part of it, because of your stepper motor has a certain step, is 1.8, further divide, having the gear ratio of 9, which goes to 0.09. So you cannot control beyond 3.5 milliradian. So if you go one step beyond your control, it leads to out of the detector. This is again second instant. So you drive again this pendulum to try out once more. You again measure the angle over here and apply the control. And this instant, you are lucky to get the signal detector. So what you are here, what something like 1.66 radian, you have come to roughly 3 to 4 milliradian. Okay, so what happens in case of these situations? See, we have come to 3 to 4 milliradian. We have not come to microradian. We have to go another factor of 1,000 down. We started with 10 radian and we have to go to microradians, almost 6th order of magnitude of the amplitude. So the next damping is from the magnetic induction drive. So we'll be using the coils here to drive the pendulum. Let us look at this now. So oscillation of small amplitudes are damped by electrical techniques. As the earlier was the mechanical techniques, and this is electrical techniques. So magnetic induction drive system used to damp small amplitudes. So the idea is that you put orthogonal oriented current coils here and drive in a quadrature, that you apply sine and cosine signalities by generating a rotating magnetic field, which in turn applies a drive torque on the mass work of the torsion balance. So in other words, it can say that in effect the coil then functions like a stator and the mass work as the motor of an induction motor. Is that principle easier? What you have to know, but this is in again a feedback system. You want to know what is the amplitude of the torsion balance before applying. You want to know what time it should be applied. You want to know which direction it will be. So there is a control system for that. I am not going to go in details of this thing, but your torsion balance here, whose motion is monitored by optical lever, PhD signal is used, circuit is used for measuring the angle. That information goes to a computer which computes the action, that in which direction, what time, and how much is to apply the drive, which goes to power amplifier. Power amplifier drives the mid coils and which controls the torsion balance. So you have two options here. You can generate the torques either proportional to the angular velocity, that you make a single measurement of the angular velocity, or you can make every instant displacement measurement and apply torque depends upon the angular displacement. So I will show first the angular velocity. So here is the program which finds out the amplitude. So this is the case where the signal is not fully on the detector. It is going out of the detector, which comes from plus 10 volts to minus 10 volts. So you find out how much time it has spent onto the detector. From that, you will know what is the amplitude. So you know the time spent here and you find the angle there. Okay. And then you know what is the direction of that and you know what is the time itself. So it gives the current time and it gives the drive on time. In this case, the drive is applied in a half sinusoidal fashion for a half period of the torsion balance. That is, you start at the extreme of the torsion balance position. By the time it comes at the center, it takes half the time. It is supposed to go to the extreme, but you have applied the drive torques to slow down it. So what it looks like is somewhere like this. So here it was on the detector where you measure the transition time, and here you apply the drive torque. The drive torque for the mid is given by this formula K by square root of root T, and the TO is the transition time. This is found empirically. I have not understood this for what reason, but I played with it and I just used that transition time to fit into this formula where if I give K value as 1.8, it just slightly under damp. But if I give K as 1.8, it just comes at the mean position and stop. Of course, there is some oscillation, but if you increase the K value, it is over damped. But now, in any case, you are on the detector and well within the 2 to 3 milliradian. The next control comes from the drive trucks applied with the proportional to the angular displacement. In this case, you apply the drive trucks looking at the displacement at every instant of every seconds. So drive trucks will be applied K times the delta x, and delta x is the displacement of the light spot onto your horizontal detector. So this is the oscillation, which is close to 9 to 10, 5 to 6 milliradian. This is without damping. When you apply damping with K value is 9.5, this is under damping. See, the oscillation cycle is supposed to be 1000 seconds, but this has keep on oscillating. If you increase the K value, this is over damping. It has taken a long time, almost 2000 seconds, though it is damped, this is over damping. But as you tune the parameter K, you eventually end up with close to critical damping, where within one cycle, it has come to the mean position. So if one tunes the system properly, one eventually get with a flat line over here. I purposefully kept it like this because I have to run my second application on this, and just to show that it is almost there, which is showing period of oscillation and damped well within the 10 of or 15 microradian, which we have reached. Okay, so now we have completed the second part of the control instrumentation, which is damping of motion. Now you might have noticed everywhere I have put the voltage output, but this is not the correct way to show. We have to tell the angle in terms of, we have to tell this in angle, not in voltage. So we have to calibrate our optical lever to what voltage corresponds to what angle. So that's what I'm going to talk about the thing next, which is also an automated system. What we use is a compensating plate to calibrate our optical lever here. So as again I said, optical lever is for the non-contact measurement. It is necessary to calibrate the system periodically. See, everything has a drift associated with time, and whatever best you try to eliminate all the effects, they will be still there. So it's a good practice to periodically calibrate your system, whether it's an instrument or some measuring like optical lever or your control systems or whatever it is. Okay. So in our case, we have a compensating plate. This picture may not be very clear, but I will show in a schematic way much better, which is used for calibrating the optical lever. And this calibration has to be obtained even while the torsion balance is oscillating the motion. So the torsion balance is moving, and yet you have to get the calibration done. You can see in the background there is a thermal enclosure, so you cannot get into all these things for driving these things. So we have to automate this system. What we use an encoder micrometers to move the calibration plate. Okay, so here is the schematic of auto-calorimeter. You have a light source. The beam goes through a collimating lens. It is collimated, a parallel beam coming out and hitting a target mirror. This is the mirror onto the pendulum. The reflected beam comes back. The same optics is used to again focus the image onto the detector. And as the mirror translates, see if it is translated in a horizontal direction, no effect. But if it is twisted, then only there is an effect. So it is not sensitive to the translation straight, but it is sensitive to the angles of twist. So if the mirror gets displaced by delta theta, that results into the spot changing over by delta x, and there's a relation between that. The delta x is depends upon the focal length of the lens and the delta theta, how much is the mirror move. Now you assume that this is a fixed mirror now, and this delta theta you have to mimic by the compensating plate. So you have to move a compensating plate in a such a way that you generate very precise delta thetas, so that you know how much angle corresponds to what voltage on the detector. So there is a formula here, and the phi is the angle which is you want to move of the compensating plate. These are the parameters of the formula, that is F is the focal length, T is the thickness of the glass plate, and N is the refractive index of the glass. And psi is the angle by which you push the compensating plate. So you use encoder mic, and that can able to generate the rotation at the level of arc-second level. So eventually you can get this angle as small as few nanoradians. So you have to translate this compensating plate as a nanoradian region. So while if the torsion balance is oscillating the motion, you would like to obtain the oscillation the calibration at the turnaround time of the torsion balance motion, because at this position the torsion balance is almost like a steady state. You have reached to the 10 microradian oscillation amplitude, but still there will be an amplitude to that. So you have to make sure that you are doing it at the turnaround time of the torsion balance motion. That is one thing which is crucial in this. And then after finding it that condition, you have to evoke the driving of compensating plate, record all the data from the your optical lever along with your encoder mic, and then obtain the calibration for this. So we have a test setup in Mumbai lab. I'm just showing you the one photography. So this is the our test setup. Inside there is the pendulum. These are the coils here, and there is optical lever here. And next to that is the instrument rack. There are 5 components all together. All is home built here. The first one is the circuit for processing circuit for the optical lever. This is for the stepper motor. This is for the encoder mics. This is for driving the coils. And this is the NI hardware used for interfacing with computer. And this center unit, which interfaces NI hardware with all these instruments. So I'll just show what are the applications one can run with this interface unit. So you have application like MID, that is driving the mid coils, or mics. This is just a short abbreviation of the encoder mics. So you can decide which application you want to run. Whether you want to damp the amplitude, or whether you want to correct the drift, or you want to calibrate the system. Now, in case of drift correction, we are going to see that we have to use the 45-degree mic, and in case of calibration, you have to use compensative plate mic. Now you have the functions here, which I will explain later, that what is the recovery mode and what is calibration mode. In addition, you are given whether you want to do manual calibration or auto calibration. Mostly we do in auto calibration. And in manual calibration, you are given the entire control of the encoder motor mic. And this gives the system status. These are the output for the power amplifiers. These are the input coming from your optical levers. Okay. So we use the state machine architecture programming in LabVIEW. The state machine architecture gives you hands of passing individual actions onto your application. For example, here, this is the program for controlling and monitoring the motion of torsion balance in gravitation lab. The moment you launch the program, it will give you date and time, and then you have this application which you can select. Like you just can decide to just monitor the motion, or you can decide damp the pendulum, you can decide drive the pendulum, you can reset the signal, you can calibrate the optical, or you can recover the signal. And the parameters are shown here, that how many cycles have been done, what is the reset signal has to be corrected for, what is the calibration range, and things like that. Here you get the amplitude and the offset into the system, and the data is written in the file. The center part is used for the instruction. Any new person who wants to read and go through what the program does, it is written over here. And here you get all the task updates and error updates. If some error happens, the red LED indicator comes and tell you that this particular switch is not on, or this is going out of the line, or like this. Now what I'm doing here is I'm checking for the turnaround condition, because I selected calibrate the optical lever. And I will show you the next how a calibration goes. So it has find out the turnaround time, and it has driven the encoder motor mic. It has recorded the voltages of optical lever and of the encoder motor mic and the LVDTs, and give you the calibration, and it is written in the file. The second application I selected the drive pendulum. So it will show here that driving the torsion pendulum in which direction. You give the direction information, so that it is clockwise. And if you see here, now it is close to 0.5 volts peak to peak, which is driven to plus minus 11 volts, almost 22 volts, and very precise you can control. depending upon how much drive voltage you're applying and how much time you are giving for the drive. So very precise control on your torsion balance motion you can have. Okay, so this graphical shows all the actions of this program. Like you can drive. In case of drive, you have to apply the drive when the velocity is maximum, and in case of damp, you have to apply the drive when the velocity is minimum, that is the turnaround. So the program has to find out when it is passing through the highest velocity, and here in this case 0 velocity, and then apply the damping force. This is the offset. You know, there are time dependent drifts. I will come to this in later. You would like to correct for this offset. So it finds out what is the offset into the system, that is the mean position shift, and it's correct for the offset. This is the calibration, where you obtain the calibration of the optical lever. And these are two things where you're showing that by chance something goes wrong in your program or things like that, the compensating plate maybe get driven beyond its limit, and you should not lose the signal. In that case, the supply for the encoder motor is provided through a limit switch. The moment it goes beyond this limit range of the optical lever, the switch opens, and the program find out initially itself where it was and parks back this compensating plate there. Same thing happens on either direction. So this is very important, because once you lose the signal, it's very difficult to get back. So this is the safety precaution which has been inbuilt into the system. Okay, so I'll show you in more details about the calibration, because it's not very clear over here. What we talked about, that we want to obtain the calibration at the turnaround time, but when? After the turnaround, before the turnaround, or exactly the turnaround. So there are two conditions I'm showing here. This is after the turnaround, and what you see here, you see the calibration is, here is the milliradian angle, and it is the output volts. So 4.7 volts per milliradian is the calibration. What happens if you do just before the turnaround time? And that's what is being shown here. Now you show all the points lying on the line. The R-square value itself tells, and the calibration value is almost 2 to 3% more to compare to this. So it's always good to evoke the calibration just before the turnaround, so that you maintain at really very flat portion of the turnaround and not at the rising edge. This contributes to the error. Now there is one more error which happens, and which I will show now here. Well, you have successful doing at the turnaround time, you have programmed it well, but when you are parking your CP, that's compensating plate, when you are driving the electromagnetic, it may happen because of the mechanical backslash of the forward and reverse direction of the motion and things like that. You may not end up at the right place. So for example, in this case, it doesn't hit exactly park at the same position. In this, it has happened. So it can be give some kind of offset. And imagine a case where if you keep on calibrating your system on day-to-day basis, you may end up providing drift into the system, and such drift should be taken care. So that is the fourth part of the control system, which is the drift correction. We use beam steering mirror again to correct the drift. So let us look at that. So we use a 45-degree beam steering mirror to correct the drift. Encoder micrometer is used to tilt the meter. So we have the encoder micrometer, and there is a mirror over here. Looking at the drift rate, we can predict also this is time dependent drift, and of course drift introduced because of our calibration process. So we want to keep track of this, that how much drift we are correcting as it's day to day, so that one knows, we can do a prediction that after so many days or week, one has to go and correct for this much drift. The commercial controller what we have doesn't have this feature, that you don't have any memory. You just lost the moment you switch off, everything goes. And we could not find anything in market, so we decided to develop our own controller. So before that, I will just give a quick information about this encoder micrometer. It has a DC motorized actuator for translation purpose, and an instrument encoder for position information. The key to that is it has a very fine pitch screw which moves into a threaded portion, and with a gear ratio of 485:1. So when the motor runs when 485 tons, this gear runs by 1 ton, and the pitch of is almost 0.48 mm. So which gives you a sub-micron resolution readout. So we use encoder micrometers from the encoder Oriel, but we developed our own system. Now here is the total block diagram of the full system, and I will not go in the full details of this thing, but there are three major components to this. First thing, you have a mechanical system under control like compensating plate or the 45-degree mirror. So the DC motor moves that, and we use a driver for that, which works on a pulse width modulation. Then we want there's a detector which is an optical encoder, and we want to measure the pulses from this. So this is for the measurement of the position. And the third part is the memory, which is inbuilt into the circuit, where you can send the data of this encoder my position into the memory, or you can feed the position from thermal switch, and you can display the position of the encoder mic. So there are three basic components. If anybody is interested afterwards, I am happy to share my details of this system afterwards. I will just jump directly to the final product. What we have made, that we have made sure that every time there is a power off, you keep the memory written. Then we have built for the two different micrometers, because we have one at the compensating plate, one at the 45-degree mirror, and each has a separate memory inbuilt. What we can do is further, it has the ability to preset a starting memory. For example, you have corrected the drift and you reach to the next step, then you will require to reset something. So you can preset the starting position. I want to start from there. So you pass that information into memory and your counter. Or we can seek a target position. This is important while you're calibrating. When you're coming back, you want to again hit at the same place. And this is all possible because at the heart of this block diagram, there is the IC which can be used for many of these applications. Okay, so our controller, I have a piece over here. Anybody wants to see this one, which is homemade in TIFR product, can have a memory inside, can give a target position, and give the position here. It has an auto mode. It has a mode for connecting to encoder motor mics, and it doesn't require anything. Just you plug in a 230 volts over here, and there's a complete manual written on this thing. Anybody has any application for in their labs for positioning their optical components or fibers and like this, they're welcome to take from me the technology which is inbuilt over here. So our controllers are minimalistic, standalone, and therefore ideal for rugged field use. So that brings me to my instrumentation part of it. Now I will share some of measurements which have been carried out just for the testing purpose. Please note that these measurements are done at Mumbai lab. These are done by the optical lever, which is 10⁻⁷ angle resolution, while the Gauribidanur optical lever is 10⁻⁻10 radian resolution. So there is 3 order of difference. But just for the interest of general people, I will show some of these measurements. Okay, so this is the program for data acquisition which you have developed. The first part of the program gives our operator or the user the choice of how many scans one want, what kind of interval one want, what is the channel delay want, what is the file, and this display all the time and date, the number of scans, and so on. This is to do with the hardware, that you have to select what channel you want. So whether optical lever oscillator, optical lever frequency, the barographs, the tilt sensors, we have some circuits and transducer for keeping monitoring the environmental parameters, which is very, very crucial in our experiment. I didn't emphasize on that point because this is not the talk about the measurement instrumentation of the experiment. That can have some time later. But we keep track of magnetic field, the temperature, the tilts, the barographs, the relative humidity, and all these things. So you can select what things you want to measure, and this gives at the instantaneous value of those things. Like this gives a frequency of your oscillator, which is very important to keep, because we have to use we use a lock-in techniques in our instruments, mostly in the optical lever and temperature measurements, in magnetic field measurements. So we have developed in-house all these techniques. So the first signal what you see here is the electronic oscillator. The period is 1 millisecond. The second over here is a mechanical oscillator. The period is 862 seconds. And the third here, what you see is a temperature which is changing into the daily variation, like 86,400 seconds. This is the magnetometer circuit output. I purposefully put my phone there so that I will know that this is sensitive. Otherwise, you will not know whether it's reading or not. But I will show you more details of this reading in coming slides. Just to make a point clear that you see very clear oscillation waveform here of the torsion imbalance. Is that reality? No. So this is just one complete oscillation cycle of the torsion imbalance here. And if you look at this here, it looks like this, something like this, very noisy. So these are the ground vibration, and these are the pendular mode oscillation of the torsion pendulum. Torsion pendulum has, other than torsional mode, the pendular mode and the violin mode. The violin mode gets finished very fast, but the pendular mode remains there. So there are two frequencies into this system, and we know if it doesn't have the proper rate of acquisition or the sampling, you will end up with the aliasing, and this is not what you see. Now, this is nothing to do with the modulation, which the equivalence principle, but this is just an artifact of your measurement rate of this thing. So one has to hit the correct rate. This is just 2.3 second rate, and if I just make the rate, which is 2.292 seconds, 8 milliseconds difference, and you get hit onto the right mode of these things, and you get very stable signal over there. So this is where you have to do a lot of signal averaging, noise reduction by proper filtering and things like that. But these are not the topics of this talk. I will now show you some measurement which is carried out into the lab. So the first thing measurement was done with the fixed mirror. We don't look at the optical lever. We don't look at the torsion pendulum, but look at the fixed mirror in the optical lever. And what you see is that output is just falling down. What is this effect due to what? This happens because of the temperature. So if you recorded the temperature at the same time, so as temperature falls, there's a drift happen missing. See, temperature just don't only couples with the torsion pendulum. It couples with everything, electronics, mechanical, all things get. And that's the reason one has to worry about the variations of ambient temperature missing. So, and then you see this daily variation. So this was done on a weekend, like you go on Friday around half a day, and then by that time you come and it starts showing this daily variations of the temperature. We were recording with the magnetic field. Magnetic field also supposed to have daily variations, but there is something funny you see here, and this is some event happening in the neighboring lab. I found out it afterwards after searching around that why this is a very systematic signal. I will show you more blown up version here. So we use 6 flux gate sensor, and all things are showing the signal. You may be wondering that why there are different levels. The reason is I have put these sensors in a stack and inside a magnetic shield. So the penetration of field decreases and is going into center of this thing. So the center one is showing very less field, while the extreme ones are showing large field. Just I thought I will share with you the beauty of the measurement instrument we have and their resolution and their capabilities, what we have built. And I'm proud to be part of this thing. Now I'm showing the signal from the torsion balance. What you see here, this is almost 10 to the power minus 4 radian. And the amplitude is damping and it is drifting. And again, you see here somewhere it is increasing and it is drift has changed. So I was wondering what's happening. And this is 0.46 days, that means morning 10 o'clock. And 0.6 is that evening 6 o'clock kind of thing. One looks 0.5 day is the 12. So I got the doubt that, oh, this may be because of I am in the lab coming morning sitting here, then I'm going for lunch out, and then I'm coming and sitting next time. So next day I decided not to stay in the lab, but just to enter into the lab and go out. And it's very quiet. So the moment I entered, it has started showing drifting. And the moment I went out and it turned up for that day, and it was showing. But how to make sure why it is happening? Is it because of the thermal potential? So I acquired the temperature also in the next run of this thing. It was going on for the days again. You can see the 4.2 days and 4.45 days. For all those 4 days, there was no much change, very little up down. But the moment I entered into the lab around 9:30 in the morning, it started jumping. And as I waited for a long time, so a certain 1 hour or something, it has started beating it. So it's very clear that temperature causes most effect onto the motion of torsion balance, and that's why we have to control the temperature in our lab at the underground better than a millidegree, which was very crucial and which was very hurdle in our measurements, and we are able to successfully suppress the waves in our underground laboratory. Now I will show you something different measurements which has nothing to do with temperature. Again, here you are acquiring the data. Now I have not damped it down to microradian, but kept it some milliradian so that temperature wasn't show much effect on this thing, so that I can peacefully work there. What you see is that the amplitude is damping. Okay, that's natural phenomenon, and there's a drift. So this is what I'm talking about, the time-dependent drift. And if it is increased, then one has to correct for it. And it's well rate is well known. But something here you see which is very different. So I just enlarge this thing. So it is very quiet over that time, and suddenly it's decided to go away, and the amplitude also increases. I don't know why this happens. It is very strange behavior. I thought that it's because of the magnetic field. I searched around in the other labs, but nothing. So this happened on a Sunday morning. That is another thing. But the good part of it that now we know how to correct the drift, and it's all done auto. The moment goes beyond around to the mean position to 0. I shifted below 0, the peak, it will correct for the drift, and the further after correcting drift, the program will damp it. Now whatever amplitude you are, whichever direction you are, it will bring back to the 1 microdegree, and that's what we finally achieve. So that brings me to the conclusion of my talk. So what we did. First, I have shown that gravitation experiment suffers from environmental disturbances due to man-made as well as natural causes. Okay. I have emphasis on the necessity by to actually reduce the amplitude in a sensitive torsion balance oscillator. And how we did it? The oscillator motion is recorded and processed digitally in real time using a series of photodetectors. You have seen those in my presentation. And the position signal has served us to generate an electronic feedback signal that controls the amplitude of oscillation. And most importantly, the combination of electronic hardware and the software, you saw a lot of LabVIEW programming with the mechanical arrays, has provided enhanced speed and position and the torque control. So the lesson is damp to detect. Unless you damp, you will not be able to detect. So that brings me to end of my talk. I have a last slide. So I would like to thank Professor Ramnath Kaushik. He's given me the opportunity to work in such a nice experiment where I could touch all parts of the scientific experiment, right from optics, mechanical, vacuums, electronics, control, and very rare person will get a chance to touch on all these things. Professor Tandon in initial days, learning from a lot of in electronics, in mechanical systems. Dr. Krishnan, of course, I have associated with him for 34 years. And I learned a lot, I owe him a lot. And Professor C. Sunni Krishnan, who is a friend, guide, and everything for me. And my colleagues from Gauribidanur Field Station for their support, help, and cooperation during my visit to Korea. I'm through. That's all.
Thanks very much, Simon. That's a very beautiful talk. Very, in a way, I must say, very characteristic style and the work, of course, that goes without saying. What has produced such a wonderful piece of machine equipment. But what is also heartening, of course, is know that every piece of this devices, the instruments are made by locally, indigenously in your lab, and the results are all there for people to see. This is, as you yourself mentioned, 2012. We still remember this particular talk that you gave on the thermal control system, and this talk is very, very similar to that in terms of the details, the care with which you took and built these beautiful instruments. So congratulations to you and also your team for this nice work, but also for this beautiful colloquium today.
Just
So are there any questions?
To add that,
Yeah.
I should stress here that all this automation of these instruments, which Simon talked about today, when we were doing the thesis 30 years ago, we had to do it manually, going underground, 25 meters, sitting there, everything. And what Simon has managed is to automate everything in this experiment, and it's a remarkable achievement.
Yes, absolutely, absolutely. I fully agree. I mean, also one could see that the thing is that you understand what you need to control, you understand the physics behind, you find the right transducer, the method, find out the real digital or analog and digital instrumentation. But very important is to solve problems one at a time. And it's truly remarkable, the entire work. Of course, as he rightly acknowledge the team of people who are behind in some way and motivated the entire team of engineers. It's amazing, amazing piece of instrument. I mean, I have no words to kind of say beyond that. But so that, okay. So, but let me see if there are any questions from the audience, also from the Zoom. By the time others ask for, let me ask Simon. So you did mention that this is something quite, in that sense, a little general purpose and probably find applications by other groups and laboratories. So are there any groups in TIFR which has utilized your expertise or instrument? And
yeah, a couple of people have asked me for like stepper motors, and I've shown the stepper motors like this. Not exactly for the encoder, but I'm sure people may not be knowing about this thing. So in fact, I have a complete manual written on this. People want to refer, the all details are given in this, where they can use this instrument. Beyond that, we don't have a way where you can showcase your product and people can make use of these things. Okay. I would happy, I mean, if people want something like to move something at submicron level position, using whether stepper motors or DC motors, I would like to help in this.
I mean, maybe just an extension of the same question. So, did you happen to kind of talk to any other institutions, or even better, if any industry that would need such kind of instrumentation?
No, I mean, today I talked to Mr. Khurana, who was from Khurana. He said that you can take patent for this because this is something new, and this will have a medical application where drug deliveries and things like that. And I happened to talk to Dr. Krishnan about this, and of course he suggested me that your process of characterizing thermistor. I mean, if you look at thermistors, they claim that they are at 10 millidegrees, and we are telling that we did at 0.6 millidegree. So how is that? It is because of the characterization of our process what we have established in our lab. So I talked to Krishnan, but Krishnan said that we are here to do research and not doing this patent and things like that. I mean, yes, okay. So we don't look from that commercial point of view of all these things. So we really didn't look at that.
No, I agree with Krishnan. That is a basic motivation. But having developed, I mean, I don't think anybody, for that matter, institute or anybody kind of stops you. Institute now, I mean, encourages people to kind of not only patent, but also look for potential applications. I mean, there are many obviously successful stories now, the so-called resource generation and technology transfer initiative of the Institute. There are opportunities, and I think you should seriously think of talking to people and industry, and also the other like-minded laboratories where this can be kind of taken up. Okay.
Yeah, it's a good
you may remember, actually, Acharya has a question or comment. I will ask him to say, but you may remember recently, or KV Srinivasan from LTF, the kind of work that he has done. There was a good amount of, he also gave an asset colloquium, and there were lots of things that came up, and I think there was a progress on such instrumentation. So I think you should seriously think about it. Yeah, Acharya, can you please ask?
Yeah, Simon,
Yeah,
What further improvement you are planning now?
Well, I mean, there are certain issues regarding to the mechanical structure of the, at the Gauribidanur.
Hello?
Yeah, I lost you.
Scope of doing something. So you saw the attack is programs or the control programs.
Now.
Yeah. Yeah. Do you want to ask something further?
Yeah, Simon, towards the end, I think your this one is not very clear for question to Acharya.
Okay. So he asking whether what is the next improvements into my system, no?
Yes.
Yeah, that's it.
Yeah. So right now I have nothing is clear as what kind of a future of the Gauribidanur experiment. So that's the state.
Okay.
Did I answer your question?
No. I was asking from in your area, what improvement you are trying to work on for improving your system. Your suggestion as well. Your suggestion as well as your plan.
Yeah. So I mean, I did myself train for the FPGA based instrumentation. In fact, I built something, and I didn't show because that is not a part of a research activity, I think, but where I measured just for the sake of what is the G. I mean, you all know that G is 9.8, but do you have seen somewhere kind of G? So I used that thing, FPGA board, to make a G value measurement, which is good up to the 3rd digit precision. So that's what I mean. You try to learn the new technologies coming, and which can be will be used in other groups or department also. So that's what I was been.
Yeah. Okay. Yeah. Very good. Yeah. Good.
Okay. Are there any more questions? Unni, do you want to say anything more?
Yeah, in some sense, what you pointed out about the technology interface, I think the fastest connection is between motor-driven optical components and how to control them with some feedback signal. That is where Simon has really developed things which are ready to use. Now, of course, these controllers need matching motors. But one can also think of just a shuffle motor thing with division, microstepping, because Simon has expertise in that. So, and these instruments can be better than what is being used in present Indian industry is what I feel. So that is a fastest thing. But once that channel opens, just by discussing with the user and the company, Simon can definitely improve on whatever existing instrument it is. A better improved version can be generated with his experience. So that is one thing I'm sure will be in a quick channel of development. Other things are, I think, more specialized. Like thermal control, nobody in the country needs a millidegree kind of control, not even for biological applications and so on. But under 10 millidegree is available probably already. So, but control of environment, motor control, these are the two areas in which improvements can be done, but whatever is already developed is better than what is in use in typical industries, especially precision optics, optical control. And another thing which is a characteristic of Simon's instruments made by Simon is compact nature and reliability, which we have experienced, and I mentioned it. Some instruments are working for 30 years in the original environment, underground environment. So these are all important when you try to build instruments for scientific research, not for just some industrial application, but instruments for scientific research. Many institutes can be used. But the culture in India today is just to buy some commercial instruments and use them. So I don't know how much practical implementation will be there, but definitely Simon can contribute. If there's a channel open between Simon and the user through some industry.
Fantastic. Yeah, that's a very nice way to kind of summarize. So essentially exploiting Simon's expertise in the control system, in the developing very precision measurements and control, and as you also said, doing something indigenously adds a fantastic value. So with those words, and if there are no more questions, once again, let us thank Simon for this fantastic colloquium, and also wishing all the best for his future endeavors. Thanks very much, Simon. Thanks very much, Unni,
All of you participants.
for taking care of the talk.